so we have the Euler-Lagrange equation. It's a general, it arises in the calculus of variations. For the critical points. Of a certain functional, which we call the energy functional. Integral of Lagrangian. I write this with the letters gamma. Actually, you could have also the function t. And the key fact for us in differential geometry is this: the Euler-Lagrange equation, which maybe I will just simply write here in variables, in physics variables. So this is a little footnote in physics variables. And I use the notation of Arnaud. This equation is something like, if I may make a sign mistake, you can check it. Physics people know these things very well. You like it? Okay. And these are the coordinates of the cotangent bundle. You know about this now. And the key fact for differential geometry is that L, which depends on, I'll write it in physics variables, is convex, and therefore we can apply the Legendre transformation, which is a general idea. Implies that we can transform the cotangent bundle with Legendre. The Legendre transformation.
So you want to say tangent bundle, Q and Q dots?
Pardon?
Q and Q dots are coordinates of the tangent bundle.
And I put cotangent as question. Yeah. So we transform there, and that transform, we should understand that this is fiber-wise, of course. So it does nothing in Q. It only transforms the fiber. It's transforming velocity to momentum in the physics language. So the transformed Lagrangian, so that's the thing you're trying to find the critical point. It's this thing L is the Lagrangian. transform Lagrangian is a function of physics coordinates p and q. So p is momentum, and q is just your coordinate on the base. This is the transform Lagrangian, and it satisfies the ODE has become, in some sense, much simpler. So ODE is now very simple. It's Q point equals dH with a minus sign, dP, and P point equals dH dQ. You agree with my signs? All right. So that means that to solve the ODE, so these are many equations here. The index has been hidden here. Solve the ODE. We must integrate the vector field which is, I'm going to call XH here. So it's the vector field which really is associated to H, which is minus dH dQ ddp ddp. No, I did it wrong. Q point okay, d plus dH dQ dP. That's what it looks. So Q point equals that. That's how you integrate your vector field, and P point is there. Okay. That's it. So that is, so you should think of geodesics, because geodesics are the critical points of this thing, are from the local point of view, local orbits, well, orbits of the associated local one parameter group. One parameter group. That's very beautiful. It's a beautiful vector field. It's a beautiful differential equation. This over here is minimizing some integral, or at least critical points of that. Much more complicated situation. And so we study this situation. Everybody in the business studies this situation first. So the remark is, this is special. Situation of symplectic geometry. So I would like to spend at least one lecture, or maybe two, or even three, on what is symplectic geometry. It is fundamental for mathematics and for physics. So, some definitions. I started last time with some definitions. One is that a symplectic manifold, omega, is a symplectic manifold. So M is always a manifold. Here in this discussion means that omega is closed. And non-degenerate. And non-degenerate. There is non-degenerate. Now what that means is omega of x at a point x is, it's a two form. Oh, I didn't say. It's a two form. It's a two form. It's a closed two form, and so it's a bilinear thing on the tangent space at that point, and it's alternating because it's a two form. So let me emphasize that. And the mapping V goes to omega V period is a mapping from the tangent space of M to the cotangent space of M. And the condition is this mapping is non-degenerate for this mapping is an isomorphism for all. An isomorphism. For all x. So obviously there are many vectors of norm 0, if you think of this as a norm. So note, almost everything you think of at first is note omega VV is always 0. Right, because it's alternating. It's always 0, but non-degeneracy means that omega VW equals 0 for all W only when, if and only if, V is the 0 vector. Notation doesn't appear immediately here, but it will appear if you take the subject seriously. If you have an alternating form, let's say, let's make it mu an alternate two form on V, a vector space V, then the notation is V perp omega. I always use this notation, V perp omega. Those are the vectors V such that V is perpendicular to everything. Huh?
So you mean V per mu, that is your two forms called.
So if we have a two form, I want to say a general notation, first of all.
So then there should be a mu, correct? Per mu.
V, so mu is a two form on V, that's so far good.
Yes.
V perp omega V are all those vectors that are perpendicular to V.
That should be V per mu.
Oh, of course, yes. Yeah. I've saved omega for our friendly one that's with a purpose trivia. Thank you. Of course. Thanks. Yeah, okay. So that's what happens, and you can imagine, you start with a symplectic form and then you restrict it to something. You might get 0. So restriction is a very dangerous thing in this case. So maybe it's worth remarking. Remarks. V mu, let's use, I'll stay with mu here in general. Okay, this is a two form on a vector space. Okay. V mu non-degenerate, so that means that means, i.e., there's nothing that's perpendicular to the whole space except 0. That's, you clean me up on that, that's okay, yeah. But it's very possible that the restriction to a subspace vanished. It's very possible you restrict an alternating form to a subspace, it can vanish completely. Yeah. Don't forget, if you restrict a metric, a positive definite metric, to a subspace, not pseudometric, but a positive definite metric, it doesn't vanish. It remains non-degenerate. It's the big advantage with Riemannian structures. So G symmetric and non-degenerate. This was a 2 form here. Non-degenerate implies that G restricted to any subspace is also non-degenerate. I'm sorry, symmetric, non-degenerate, and positive. As you know, if you're doing with relativity theory, quite often the boundary of light cone, you restrict, you get 0. Right? But this, if you have symmetric and positive definite non-degenerate, this is saying is not non-degenerate. And still positive, of course. So this symplectic business is different from the Riemannian business. Okay? It's really definitely different. Okay, maybe that's the first remark. Secondly, let's say I'll stay in the vector space business because of course we have in mind the cotangent bump, something like that. But this vector, if this is symplectic, that means that thing is non-degenerate on the vector space. Then the dimension of this, of the real numbers, is even. Okay. You can check it. One way to well, let me just say, find a decomposition. This is the way I always do it anyway. A decomposition V equals P1 to P N of symplectic 2-plane which is omega orthogonal. Okay. And the idea of the proof is exactly what I said. But you have to, it's exactly what I'm said is you're never going to find a one-dimensional thing because it's an alternating form, right? It's going to vanish identically. But you can find a two-dimensional thing and then take your orthogonal complement and then you have this decomposition, right? So thanks. then the spaces of dimension n. So the third remark is if this thing is dimension 2, then the things right in the middle are of great relevance for many, many subjects in physics. They're called Lagrangian subspaces. Have special relevance. And they're called Lagrangian space subspaces. Bunch of words. I apologize, first of all, for that mistake, and second of all, for just all these words. So, our example was cotangent bundle of M equipped with the standard form that I introduced last time, which is symplectic, and in physics coordinates, so which Q is always the same on the base, but then momentum, omega standard is dq wedge dp. Of course, I'll remind you what that means. That means, well, Q is, of course, Q1 to Qn, so this is dq1 to dp1 plus dqn wedge dpn. Okay? So that's a standard example. And now an amazing theorem. So amazing theorem. Amazing. And I'm going to say why it's amazing from the point of view of Riemannian geometry, which is the subject of this course. An amazing fact. Okay. Let M omega be symplectic. Okay. So some abstract guy like a Riemannian, I mean, if I put here mg, that would be a Riemannian manifold. M omega is a symplectic manifold. You think it looks the same? It's a very similar thing. It's not. Be symplectic, and let's let x0 be a point of M. Let omega 0 be the standard. Somebody be the standard structure on the cotangent space. Standard symplectic structure on the cotangent space on Tx0 n. Okay, so you have a picture of, many people like to draw this picture. Maybe I'll draw it. Here is the manifold, and here is the cotangent space, here's the tangent space, and then you dualize the tangent space and you have the cotangent space. Okay. Okay. Then there exists a neighborhood say U, which is a neighborhood of x0. And a neighborhood let us say V equals V of 0 in the cotangent space at x0. And a diffeomorphism say phi from m, well, let's say u with omega on, I won't write restricted, but of course I mean restricted to the omega standard. Let us look at this for a moment. You have a structure on a manifold, a symplectic structure. You have a point. Yeah. You have a structure on the cotangent space at that point. Those are two different things, right? Those are two completely different things. That says there's an isomorphism between these two completely different things. That says that there are no local invariants in symplectic geometry. Let me say it again. You have a point in the symplectic manifold. Right? You have all sorts of neighborhoods. Everything is local I'm talking about. Then there's a neighborhood at that point. Who knows, but this is computable, actually, using technology from Jürgen Moser. The computable neighborhood of that point, that's good for physics. You really want a computable neighborhood of that point where actually the symplectic structure is nothing other than the standard structure on the cotangent bundle. The statement is there is no such thing as a local symplectic invariant. Yeah?
Yeah, I think there's a similar statement also. Let's make a similar statement on metrics.
No, it's false. It's big time false. And that's, I'm glad you said that. He said he thinks there's some similar statement. There are many statements which it should be your goal to make such a statement with a metric. Okay? But you're thinking of something I'm going to talk about almost immediately. Is there some sort of normal form, which is known to Gauss and many people, with geodesic coordinates and things of that type? But it's not a statement like this. The statement is locally there's precisely one symplectic structure locally, up to isomorphism. Okay? So you should just keep that in mind. And this was proved really a long time ago. This is proved by Dabu, and these are called quite often Dabu coordinates because these are coordinates in a vector space. Okay? And if you look at Moser's proof of this, the existence of these Dabu coordinates, it's actually in some sense constructible. Okay, so I love very much Moser's proof. Everything that Jürgen Moser did, in my mind, is just absolutely beautiful. And this is an example of something where you see Jürgen Moser's proof. So this theorem of Darboux says there are no local invariants. So symplectic geometry is somehow a global theory. It's very interesting. And in modern days it has become a global, very algebraic topological theory. It's a very, very interesting theory. So that's some remarks. So today, in 20 minutes, I will only lecture 1 hour on Thursdays. I think it's very good, and there's no stress then. Today, I will explain to you what I call the basic exact sequence. Of Hamiltonian mechanics. This subject lay around from the time of Hamilton, from the time of Lagrange, from the time of many, many physicists, and it was only picked up by mathematicians rather recently, maybe in the last 50 years. It's amazing. And much thanks go to Jürgen Moser, by the way. So the basic exact sequence of Hamiltonian mechanics. Here is the first step. We will consider a mapping of the C infinity functions on the manifold to vector field. This is a fundamental thing you can't imagine. You can't imagine how fundamental this thing is, and I don't know who discovered this, but I'm going to call this H for Hamilton. So I'm going to call this little h for Hamilton. And it goes like this. If you have f a C infinity function, smooth function, then the first thing you do is take d of it, and that's a one form. This is a one form, and in fact, since this two form is non-degenerate, df equals omega contracted with this with a vector field. So let's use the notation. Contraction is I of xf of omega. Make sure you understand that. If you have a form, you can put a vector field in the first entry, right? And you get a one form. So here, if you have a two form, you put a vector field in the first entry, you get a one form. It was a two form, now you make it a one form. Okay? And so this mapping H of a function, f, is, well, I'm sorry. I'm really sloppy today, I'm terribly sorry. Of course, it's going to be the field associated with the function. Yeah. So h of f is the field xf. Okay. Now let's have some fun. So we have fun. Okay. So let's take M to be R2. Already this example of R2, the two-dimensional vector space, is nice, because we only have omega is really just now dq dp. These are the variables of R2, those are just a pair of coordinates. And now dH equals partial h with respect to q dq plus partial h with respect to p dp. That's dH. And what that's supposed to be is you're supposed to put something in here, xh, and get dH. All right? You're supposed to find some field to put in there to get dH. Well, I mean, you can just write it down without even, you don't have to work, because this is dq, so that means that in order to get dq left over, you have to put in dp, right? So we want to put in dp, and we want to have q left over. So we want to you have to put in minus dh dp dq. You understand what I'm doing? If you're just thinking of putting these things in here, and to get dq, you see I have to get dq here some way. So that means I have to put in the partial with respect to p someplace. But dp is on the second thing, so to put it in you have to alternate it and put it in first. So you have to put it in with a minus sign, right? So that's minus that. And then in order to get the other, you have to put this in. Now, fortunately, I think I wrote the Hamiltonian equation someplace on the board here. Okay? So the point is, I use this notation purposely here because this is the canonical vector field associated to a function via the symplectic form. Okay? So it's a mapping from functions to vector fields, and then you should think to ordinary differential equations. Okay? So that's good, and it's very trivial to compute the kernel of this thing, so that we will assume that M is connected. So, and this implies that the kernel of this mapping H is just the constant functions. Right, because if D of some function is identically zero on a connected manifold, that means the function is identically zero. So I assume by now you have the formalism of exact sequence. We have a beginning of an exact sequence. So we have the sequence of maps. You're familiar with this language, or not? Maybe not. No? Okay. This is the standard injection, so I'll make it here I. So this is the injection of a constant to the constant function. Okay. This is the mapping H. Okay. And to say that the sequence is exact at this point, it means the kernel of this mapping, what goes to zero here, is exactly the image of this mapping. Okay? You need to learn this formalism, even though you're in physics. It's a very useful formalism. Deepak, you're all right on that? You've seen it. I think maybe some of you are starting to take a little bit of algebra now, so maybe you will see something like this. Okay? So that's an exact sequence. And now, that's just some formalism. Don't worry about it. So, but the key question one, the two key questions here maybe, is what is the image of this thing? So in other words, what vector fields are you getting by applying this Hamiltonian formalism to this? It's a reasonable question. What kind of vector fields are you getting? You're not getting everyone. You can see already there are special vector fields here, right? You can see that, I mean, I think very easily. So for this, I want to state today, and maybe I will indicate in the notes, Cartan's. By the way, there were two great Cartans in mathematics, father and son. It's very rare, but happens in France quite often. It does not happen in the United States at all. My son is a pianist, so it's probably better than a mathematician. So this is Émile Cartan, and the son is Henri Cartan. The son, he passed away now at a very old age, but I actually knew him quite well. So that gives you an idea of the generations, not so long. Cartan's formula. Maybe Kayvon spoke about Cartan. Did he speak about Cartan's formula no? Okay. Some people call this Cartan's magical formula. Some people call it that. I don't like to associate words like that to a formula. But it is this. It's the Lie derivative of a vector equals contraction composed with D plus D composed with contraction. That's Cartan's magical formula. And you should say the word here, this is an anti-commutator. Right? If it were a commutator, you have a minus sign here. This is an anti-commutator seen by Cartan. Anti-commutators are of fundamental interest and importance in super geometry. And if our modern friends who invented super geometry in the 1980s, or maybe slightly earlier, for example, Berezin in Moscow, had lived at the time of Cartan, they should have seen this formula, but of course they didn't. So do you understand the formula, what it means? It says okay, what does this say? So the Lie derivative, okay, what is the Lie derivative of a form? So this is a Lie derivative of a form. Okay? A Lie derivative of a form, let's say, anytime it's a general form, I don't know, let me call it alpha here to get away from these letters. So any differential form, okay? This is ddt, you differentiate it, of star inverse of t of alpha, where g of t is the local one parameter group of x. I want to make sure you understand the formula. I will outline the proof in the notes. I prove it at some airport coming back. It's not very difficult, so, but you have to think that the proof is not difficult. Okay? Just make sure you understand the formula. Okay? Contraction means put x in the first entry of the form. D means d of it. That d of it, and so this anti-commutator, okay. Right. Right. So let's today, before I finish the lectures, let's use this formula. It is the first most important formula in symplectic geometry. Okay. So df equals contraction x contraction with xf of omega. Right? Notice that d squared of f is 0. I hope you all agree with that. Right? So, therefore, 0 equals d contraction xf with omega. This equals, let's see here, the Lie derivative of xf with omega by Cartan's formula. You see why? So this plus the opposite, okay, but the opposite is contraction d. Omega is closed, so d omega is 0, so contraction d, right, is 0, so this is the Lie derivative. This says that the image of the Hamiltonian guy is contained in the set of vector fields, the set of vector fields such that the Lie derivative of omega is 0. Yeah? Now what's the Lie derivative? The Lie derivative says you act with the local one parameter group and take the derivative. Right? So Lie derivative 0 means that x is a local isometry local symplectomorphism this is actually a word, by the way. I'm terribly sorry. I don't. But the people in this business use the word symplectomorphism, and the reason is I started to say it's a local isometry. That means it's the form remains invariant when I apply it, right? But it's a symplectic form, so if you say isometry, you're thinking of a metric condition. And this is a local symplectomorphism. That leaves that thing invariant. Okay, so it's contained in the local symplectomorphism. Well, now you can laugh at me for let x be a local symplectomorphism. Okay, I'm just going to run this thing backwards now. I said, if something is in the image, it's a local symplectum. This image is going to be a local symplectum. Take something which is a local symplectomorphism. Okay, so Lx of this thing, the Lie derivative is 0. That means really it's stabilized by the one parameter group is 0. That means that contraction d plus d contraction. I mean, this beginning part of the thing you can teach a child in grade school because you apply these things blindly. So this is this, and of course omega is 0, and then d of omega is 0, so that implies that d of contraction x omega is 0. Right, because that's 0. Omega, d of omega is 0. That means d of this contraction guy is 0. Okay? But d of it is 0 means that locally yeah, locally, the contraction of x with omega equals d of f. Right? Because I hope you know the word, magical word of another French mathematician named Poincaré. Poincaré's lemma says that if d of something is 0, right, then it's exact locally. Locally. So it's exact. That means this form is the Hamiltonian of this function. So it means that we have an exact sequence. Just the standard embedding, just the Hamiltonian mapping from this. And what I'm going to call here is Ham-loc of M. Because these, yes, so these are the x such that L x omega equals 0. And those x are locally the Hamiltonians. That's a good reason to call it Ham-loc. Okay? Local, not necessarily global, right? Because there might be a problem with solving this thing with Poincaré then. Okay? So that is the mapping that goes in there, and the image of H, which I will now call Ham M. I'm trying to be consistent with the literature here. Okay, so those are the global. If you like here, I would write global. Yeah, that means they come from a global function, not just a local function. Okay. So the image is that. Okay. And now to complete, I'm going to complete this thing. So you have to practice with exact sequences. The image is not the full thing, right? Because not necessarily the full thing. In fancy words, you know the fancy words. There might be non-trivial de Rham cohomology here. So you see, the obstruction here, you have a closed form, and it may not be exact. Right? So there's a mapping here. And this is very interesting. Fortunately, this would all be French. If we, no, there are many people. Well, we have Cartan, we have Poincaré, we have Hamilton, which is Irish, and now we have de Rham, maybe you don't know, Swiss, from Lausanne. It sounds very French, de Rham. He was a very nice man, by the way. De Rham. And now what do you do here? This is an interesting thing. What do I have here? I have a vector field which is local Hamiltonian, and I map this to the equivalence class in de Rham cohomology of the contraction. Okay? I would like for that thing to be exact, right? I would like for that thing to be d of something. If it's d of something, then it's in the image. So I'm trying to characterize the image of this guy by the kernel of this. The image of this guy is the kernel of this, because the kernel of this is the equivalence classes in de Rham cohomology, so that this thing is exact. That's what I'm just trying to get. Right? I don't need to repeat that, I don't. Well, and you can check that you have an exact sequence. So, although the physicists would never write this, this is precisely what's going on. Right? This is trivial. This is a non-trivial idea. To take a function, take d of it, contract it with a form, and see what you get. Okay? That's very interesting. So, and what you're getting here is these things. So these things. Let me just write what these things are. Ham-loc. These are the local symmetries of the situation. Okay. that focuses everything. Okay? And not only that, in all of this, you have these vector fields, which are the relevant ODEs of Lagrangian mechanics, transformed by Legendre into Hamilton mechanics. Right? So mathematicians should have jumped on this many, many years ago, and they did not. They only started jumping on this with people like Jürgen Moser and in the, maybe even Moser's basic ideas. Well, Kolmogorov, of course, knew all about this. And Kolmogorov's star student in this area is Arnold. And Arnold wrote a book. It's called, I recommended it for this course. It's called, what is it called? Something Mathematical Methods in Classical Mechanics. And this is a basic book. And in the end of this book, he wrote appendices in fancy language. And he asked many questions. And these questions guided the new research in this subject, I would say, starting people of my generation. So it's a very, from the point of view of its age, it's an ancient subject because it comes from Lagrangian mechanics and Hamiltonian mechanics. But for mathematical importance, it's a rather new subject. Okay. The easy theorems have already been proved. Okay, it's always good to jump in at the beginning of something, but the easy theorems have already been proved. For example, this formalism is very easy, but okay, thanks very much. See you tomorrow for our big day.